Hi, you can see the title of today's lesson is Binomial Probabilities. We're going to be looking at the binomial probability distribution, and we need to define what determines a binomial situation, and we're going to do that with this using this little example that we have here. It says, suppose we're taking a multiple choice test where each question has 4 possible answers. You have 3 questions left to answer and time is running out. As you know, only one answer is correct for each of those questions, and you're going to totally guess at them. So your probability of guessing all 3 answers, well, that can be found pretty easily. That would mean you have to guess correct on the first of those 3 questions, and there's a 25% chance of that. And then since you're guessing, and you need to get the next one right, the and means that we're multiplying, and the fact that these trials are independent tells us that our guess on one is not going to affect our guess on the other, and therefore we can just multiply those probabilities straight on through. 0.25 times 0.25 times 0.25. I'm going to put that into my calculator. 0.25 cubed, and that is a probability. Ooh, not very strong one for you. 0.15625 for getting all 3 answers right. That's less than 2%, you guys. I don't think I'd guess. But this does qualify as a binomial experiment since there are 2 possible outcomes. Only 2. And those possible outcomes are you guess right or you guess wrong. Okay? Only 2 possible outcomes. We know the probability for guessing right. And the probability of success, we call that. And the probability of failure. If you know what your chance of getting a question right is, then you know what your chance of getting it wrong is as well. In a binomial situation, there need to be a fixed number of trials. And in this case, our fixed number of trials was 3. There were 3 questions that we were going to answer this way. A fixed number of trials. The variable that they use for that is the trials are independent, or as close to independent as you can get. Independent. And lastly, you're looking for a given number of successes in your n trials. All right, I want to put some variables here just so that we're going to use them in a formula here in a minute. The probability of success in this application is usually denoted by a p. The probability of failure, which is 1 minus p, and some places call it that. I call it q. A fixed number of trials, we're going to use n for that fixed number of trials, and the given number of successes. Folks, our textbook and myself use the variable r, although I've seen others that use the variable x. So let's see if we can put ourselves a probability distribution together for this situation. We'll remind you that the probability of success in this case is 0.25. The probability of a failure, which is an incorrect guess on one of the questions, is 0.75. N is 3, that is, we're doing 3 trials. And R is open-ended because we're going to list probabilities for all possible values of R in our distribution. One of the possible outcomes is that you guess correct on all 3. And folks, I'm going to use the letter C to stand for correct. The probability of that happening, well, you just figured that out just a second ago. It's 0.25 times 0.25 times 0.25. And what we said, 0.15625. The number of successes there was 3, or that's the R in this thing. It's possible that you could get 2 successes. You could have the front 2 be right and the last one not. 1.25 for a right guess times another right guess. This time times a wrong guess. Only 2 successes there. However, if you think about this, folks, there are 2 other ways that wrong answer could occur. That is, we could have the inside the first and the last be correct and the middle not correct, that probability would be 0.25 times 0.75 times 0.25, but you guys, that's exactly the same as this. Really, all we've done is change the position of the wrong answer, and that wrong answer could come up here and be the first of the answers. So if you think about what we're doing here, we're listing all the possible combinations of having two correct answers in there. 0.25 times 0.25, and let's figure a probability for those. All of those have two successes. And 0.25 squared times 0.75. Each of these is a 0.046875. We could have only one right answer, so the first one correct and the next two incorrect. That's only one correct answer, and you guessed it, there are two other ways that that could happen, of course. That correct answer could come in the middle, or it could come last. And both of those will have the same probability, 2 failures and 1 success. So let's figure what that is. 0.25 times 0.75 times 0.75. 0.140625. And lastly, of course, we could get no right answers. So that would be 0.75 3 times or raised to the third power. 0 correct answers. And unfortunately, in this case, that's the more common occurrence, folks. The probability there is 0.421875. Now we have listed the sample space here, all the possible outcomes for guessing on this multiple choice test. We could make our probability distribution look a little neater by cleaning it up. We don't need to have all those rows of repetition when we can just show 3 successes with a probability of 0.015625, 2 successes, and we have 3 like that whose probabilities are 0.046875, and 3 times that is 0.140625. We could just have 1 success, and the probability of that happening was that 0.140625. Of course, we have 3 that are just like that, so we have to multiply that by 3. It just happens to be sitting there, so I'm going to go ahead and multiply by 3. 0.421875, and if I recall, that was the probability also of getting no right answers, 0.421875. Now, we just studied probability distributions, and we know that they should add up. All those probabilities should add to 1. I'm going to ask you to take just a second and verify that that is the case. Yeah, sure enough. The sum of all the probability in this distribution adds up to 1, which is exactly as it should be. So there's a binomial probability distribution. You notice it's very specific, folks. For a given probability of success, a given number of trials, and then we can figure any number of successes. Let's see if we can come up with a formula that will help us find binomial probabilities without having to create a distribution each time, because you can see that that might be a little bit time consuming. In fact, there is a general formula for binomial probabilities for R successes in N trials, where P is the probability of success of 1 trial and Q is the probability of a failure in 1 trial. That formula goes this way: the probability of getting R successes in N trials, and I won't always write all of that in there. You'll see that I use some shorthand, but that's what this formula will give us. R successes in N trials is equal to, and we mentioned previously, that we had looked at all the combinations of places where we could have 2 right answers, all the combinations where we could have 1 right answer. Folks, the combinations are a part of this. So it is n items chosen our ways. That is, we're looking for the combinations of the number of trials and the number of successes that we're willing to take, or that we want to take. That gets multiplied by the probability of a success r times. That is, we want our successes, so we should have p raised to the r power. The rest of the time we have failure, and that happens on n minus r trials. That makes pretty good sense if you think about it. We accounted for all the combinations of how those successes could occur within the number of trials. We get r successes times n minus r, or the rest of the time, failure. That formula works for all values of n, r, and p and q, and binomial probabilities are so, they're studied a lot, and so there are tables available that will let us, instead of having to work this out several times, we can look up values right in a table, which is good. And I'll make sure that you get that table tomorrow. I'll show you how it works here in just a second. Let's try this example. A biologist is studying a new hybrid tomato. It's known that the seeds of this hybrid have a probability of 70% or 0.7 of germinating. Folks, if germinate is a success, 0.7 is our P here. What would that make the Q in this situation? Well, it's the rest of the probability. They either germinate or they don't. So 0.30, or just 0.3. The biologist plants 10 seeds. Here's our fixed number of trials. That's our N. Find the probability that exactly 8 of those seeds germinate. Well, 8 is the number of successes we want if germinating is a success. So the formula would say the probability that you get 8 successes, notice probability of 8, is equal to, well, it will be 10 seeds, choose 8 of them to germinate, times the probability of a success, 0.7. We want 8 successes, so 0.7 to the 8th, times the failure probability, 0.3, the rest of the time, 10 minus 2 times. Notice that those two exponents must add up to the number of trials. As far as doing the work here, your calculator can help you out. 10, and you'll find the combination key under math and probability. It's option 3 there. 10 NCR, and we want 8 successes. We need that multiplied by 0.7 raised to the 8th power. We want that multiplied by 0.3, the failure probability, raised to the 2nd power. And again, those two exponents, 8 and 2, have to add up to 10. Let's see, that probability is right around 0.233. Now, you'll notice that I have a place for us to look it up on a table. You haven't seen the table yet, but I'd like to pull it up right now. Alright, here is our binomial probability table. You can see that it is organized by n, which is the number of trials, and we have several quantities of n here. In our textbook, we use r for the number of successes. This table uses x. Across the top, some common probabilities, and you can see the probability we're interested in, 0.7, happens to be one of those. We need to get to 10 trials, however, so let's scroll through this until we see n equals 10. There it is. And we're in the 70% column, so I'm going to put an arrow right there. And what we were looking for is the probability that we get exactly 8 successes. And I'll be darned, look at that, you guys. 0.233, which is just what we said when we used the formula. Very interesting, but not too surprising. We know that the formula should give us what the table says. They are built upon each other. So let's see if we can't utilize that table just a couple of more times. I want to give you some ideas about the language involved with binomial probabilities. This says the probability that at least 8 seeds germinate. Well, folks, if you think about what at least means, that means that we would be happy with our 8 seeds germinating. But we would also be more than happy if 9 seeds germinated, or if all 10 of them did. And notice that we are adding. You heard the word or come out of my mouth. One of the good things about using the table is that it allows us to add those probabilities. They're all right in one place where we can see them. So let's get to the table again. And as I said, tomorrow y'all will have your own table. 0.233, that was the probability that 8 germinate. 0.121, the probability that 9 germinate. And finally 0.028, the probability that all 10 germinate. 4, that's 12, 4 is 8, so 0.382 if I'm adding correctly. All right, that probability, again, adding together the pieces, got us 0.382, and I would love, I think, to write them underneath. It was 0.233, 0.121, plus 0.028. All right, next, the probability that fewer than 3 seeds germinate. If you think about that, it is possible that 0 seeds could germinate, which would be very sad for us. It is also probable or possible that 1 could germinate or 2, but I think we have to stop adding there because this says fewer than 3. You don't want to include 3 here. So we have to add up the probabilities for 0, 1, and 2. And just going back here quickly, here, oh, look at that, the probability that you get no seed, that means that it's less than in this table 0.0005. Same thing is true for having 1 germinate out of the 10. And then when you get to 2 seeds germinating, 0.001 is that probability. So this was 0 plus 0 plus 0.001 for a total of 0.001 that fewer than 3 seeds will germinate. You know, that makes sense. There was a pretty good chance that any 1 will germinate. So getting 10 to not germinate, highly unlikely. In fact, that's what this says. The probability that all 10 seeds fail to germinate, folks, that would mean no successes. And the probability there is as close to 0 as we can get. Now we'd like to add some information to your knowledge about binomial probability distributions. As we talk about a probability distribution, of course we're interested in its mean and in its standard deviation. And for a binomial probability distribution, the mean is easy to figure. We use the population mean because we're talking theoretical, and it is the number of trials times the probability of success on any one trial. So the mean in a binomial is n times p. The standard deviation, the sigma, for the population standard deviation is the square root of n times p times q. Number of trials, probability of success, probability of failure. Good. That ends our discussion on the binomial probability distribution. Tomorrow we'll look at a series of problems about it. I hope that you'll get out there and do that. You try before school tomorrow. Have a good evening.